The bottom-up method is a linear perspective grid system that I developed to serve as an in-between to sketching and creating grids. I want to point out that, although I am familiar with several methods, I have not seen what I'm about to describe here, and that to my knowledge, this is original. In the past, I have spent years researching to find or make a specific method or another, speaking to engineers and eventually creating a system, only to find out sometime after that one already existed. So I realized that with the bottom-up method, the possibility persists. The techniques used here, such as using the diagonals within a rectangle to either double or half a space, are clearly not my own, but have been in geometry and drawing for a very long time. It's their application and the resulting process that I think is new. For the purpose of this discussion, there can be said to be three basic approaches to linear perspective. This can also be applied to symmetrical and curvilinear perspective, but that's outside of this scope. These are not official terms or definitions. Instead, they are just used in this example to differentiate. The types are direct measurement, geometric construction, and observation. All of these names are arbitrary since these approaches are all based on geometry, measurement, and observation, but some lean more to one approach than another. There are many approaches to linear perspective and many views on how to think of it too. I think of linear perspective as all being in either 1 point or 5 point for curvilinear. The simple reason for this is that to some degree, that is how a man sees the world around him, and the camera as well, even if it's not completely accurate. Like any other system, it is a shorthand, and in my view, one that is a more accurate perception more often. Within this paradigm, objects rotate instead of the view. A similar archetype can be found in architectural drafting methods of old. At some point, it became popular to rotate the view or position of the camera at least in the X or Z axis. If X is the breadth, Y is the height, and Z is the depth. Rotation is still performed on the Y axis, however. An idea that has permeated into the popular industrial design approach that seems to be ubiquitous today. This accompanies the ellipse that remains ever so stubbornly within a limited field of view or cone of vision. Then the resulting squares do not conform to the distortion from wide cones of vision. Probably the best ellipse method I have seen involves using 2 ellipses per side of each cube, but I still think it suffers from the ambiguity of other such popular approaches, as well as the compelled slavery to a specific cone of vision. In the following examples, the term cube is used rather than box, because the resulting box will have all equal sides. GIMP is used because it's not as accurate as Inkscape and should replicate the level of accuracy while drawing traditionally, and also any situation where there is not absolute accuracy, including other types of software. It is accurate enough to have alignment to pixels, but often the actual placement of a line falls between pixels. Although off, it's not enough to ruin a drawing. Afterward, IBIS paint on a small touchscreen will be used to draw the cubes with fingers, again to lower accuracy. Although accuracy will be on display as vanishing points are aimed for, the same issue can be observed when drawing a cube with an ellipse first technique, but an example of applied exactitude will be exhibited. To conclude, Inkscape will be used to demonstrate the bottom-up method in an environment with more accuracy. It should be noted that this method is better suited for traditional drawing, whether freehand or using a straight edge. Second to this, Inkscape or an equivalent vector graphics program would be the next best option. In the coming examples, these basic steps will be performed and generally outline the process for the construction for the bottom-up method. Number 1, draw projection under the perspective drawing. Number 2, draw bottom plane and projection. Inaccuracy here will result in the incorrect height of cube. Measure at horizontals. Number 3, mark heights of legs and corners. Measure the horizontals where the corners of the rotated cube touch the inner square. These are the heights of the corresponding legs. The heights can be measured, then those measurements can be replicated at 90 degrees to get the height, or a line can be drawn to the length of the reference line and then be rotated and placed. The important part here is that the height lines be taken from the width of the unrotated square. Number 4, draw sides and top of cube. Number 5, extend to check vanishing points. Number 6, define boxes. Number 7, draw ellipses. Drawing a cube rotated at 45 degrees on the y-axis, then 45 degrees on the z-axis. Number 1, drawing the projection plan. Draw a line parallel to the horizon. In the future, this line does not need to be parallel to the horizon. It is here for the purpose of making an example. This line will be the start of the projection for the rotated cube. Extend vertical lines down 90 degrees to the first line. These will be the width of the orthographic square. Allowing space above this square, about 1/4 to 1/3 of the orthographic square, should be enough for rotation. Draw the square A, rotate or draw a rotated version of that same square at 45 degrees. Enclose the new rotated square within the box B. Transfer the sides up to the first horizontal line. Draw an X from each corner of the smaller unrotated square and the corners of the bounding box around the rotated square. Lastly, add a line dividing the first square vertically in half and then another horizontally. Rotating an orthographic square. Here are a few ways to rotate the orthographic square. In software, on a separate layer, the square can be rotated from its center to the desired degree. In software, on either the same or a different layer, each of the sides can be copied, pasted, rotated, and then placed. On Canvas and in software, on the same or a different layer, each side of the square can be measured and redrawn. Or a circle can be placed centered on the square with a radius tangent to the corners of the same square, then each side can be drawn to any degree. Number 2. The bottom plane projection. First, a line parallel to the horizon A will be drawn to set the lens. This rear line will form the box that holds the rotated square. Then, using the diagonal lines, the smaller square can be found where the diagonals intersect with the converging lines. This will be the corners of the unrotated square, sitting on the bottom projected plane of the rotated cube in perspective, the Y-plane. The convergence B is arbitrary. Once the first line is drawn, setting the convergence, the others are measured to match from the center line. Here they have been measured with GIMP's measure tool. The first distance, or width in this case, is the square without rotation. Then this distance can be doubled and then divided, or a line can be eyeballed here in between the line of the unrotated square and the line of the bounding box for the rotated square. The amount of accuracy in this step will determine the accuracy of the height of the cube. The converging line in between was started at the projection, and the placement of its far end was estimated. Drawing a line between two near lines makes this easier. It's worth mentioning that the squares projected on this bottom plane do not need to be at the bottom line or the line nearest the viewer. They can be drawn further in perspective away from the viewer. Number 3. The height of the rotated cube. Mark the heights of legs or corners on the bottom plane. Measure the width of the unrotated square in perspective that is directly aligned horizontally with the corners of the rotated square in perspective. These are the heights of the corresponding legs and are drawn on the corners of the rotated square that's in perspective. The heights can be measured, then those measurements can be replicated at 90 degrees to get the height, or a line can be drawn to the length of the reference line and then be rotated and placed. The important part here is that the height lines be taken from the width of the unrotated square. Number 4. The sides of the cube. From the corners of the rotated square, draw lines up vertically to meet the height marks of the cube. Connect the four corners to complete the cube rotated 45 degrees on the y-axis. Rotating the cube 45 degrees on the z-axis. In this example, the orthographic plan is drawn on the right of the cube, but it could be drawn on either side as well as within the walls of the cube. This is also true for plans using diagonal lines to divide space, or wherever it would be most convenient. Number 5. Extend the plan. In this example, the right rear edge is extruded to the right orthographically. Again, some space is given between the cube and the square to accommodate the square that is to be rotated. Construct a square within these horizontal lines and pull diagonals from the corners, extending those same diagonals to reach the bounding box for the rotated square, and extend that box to intersect the resulting vertical elongated right edge of the cube, along with any other horizontals needed for measurement, such as the midline and any edges of either bounding box. Number 6. Extend the cube. Where the horizontal lines from the bounding box of the new vertical rotated square touches the extended upright edge of the cube lines, draw lines that match the convergence of the lines on the right face of the cube. In other words, lines that would be aimed towards the right vanishing point. These lines would be drawn towards the left. Next, the diagonal lines on the right surface of the cube need to be extended as well. At the point these intersect, the new converging lines mark new verticals describing the sides of the bounding box for the new rotated side of the cube. Take the lines from the vertical plan where the rotated square intersects the corresponding bounding box to the converging lines, then transfer them to the new face on the cube. Since, in this case, the rotation is 45 degrees, the center horizontal and vertical lines can be used to mark these points. Transfer the heights of the new side belonging to the cube to the left or far side of the cube. From these positions, draw lines matching the convergence to the imaginary right vanishing point and close the new rotated cube. The main idea is that the unrotated square on the orthographic plan should be used as a reference for any dimensions on any side of the rotated square when applicable. Aside from this, the rest should fall into place. Therefore, the particular geometric techniques employed are of less importance. Strengths and weaknesses of the bottom-up method. Strengths. Squares and cubes are not tied to an ellipse, that is, itself adhered to a cone of vision. Takes less image area than a complete grid. Lends itself to freehand sketching. Rotates a cube and not the view. Rotates the cube on all three axes. Can arbitrarily change lens or cone of vision. Weaknesses. Takes more image area than using an ellipse to create squares. May be tedious on digital art software. Not as fast as using an ellipse. More grid work than starting from an ellipse. Cannot be set to a specific lens field or cone of vision. Now some other examples of cubes in different rotations. The process is the same following whatever degree is chosen. Presented here was a sort of bad case scenario where accuracy could not be ascertained. Next, the resulting veracity will be tested and demonstrated. This will be exemplified on these cubes made in GIMP, as well as some made in IBIS Paint, which were constructed using fingers on a 6.5-inch screen. Afterward, a more accurately rendered cube will be drawn in Inkscape to establish what is possible in a better situation, therefore covering a spectrum of possible instances. This is a test of where the vanishing points would fall. In these specific drawings, there will be some amount of errors. It should be pointed out that when trying to find some of the vanishing points, there might be one line that misses in these occurrences. 3 lines could be right on, or all 4 could be off by some extent. Ellipses are placed into some of the facades. IBIS test. In this case, arcs serve as the measured line segments previously in GIMP. Again, the exact technique is not as important as the main concept or the outcome. For measuring convergence and the transfer of measurements. In GIMP, the measure tool can be used, and in Inkscape, spaces can be divided using objects such as circles, or by drawing lines that snap and rotating or duplicating those lines, as well as using arcs. With traditional media, a thumb can mark a drawing tool. A piece of paper can be folded. A straight edge can be marked. A marked straight edge can be used, or even a compass pair. All of these and more can be used, and in different ways. This is the same type of application with a different approach in Inkscape. The bottom orthographic plan is generally plotted in the same way. The convergence of the first 2 receding lines are made symmetrical by using Inkscape's built-in ability to snap to specific intervals of preset degrees, in this case 15 degrees. Next, the total width is marked with a rectangle, then a new section is added in this rectangle to mark the smaller bounding box of the unrotated square. This rectangle is then taken back in perspective by scaling it down to fit at the desired position. Then it's duplicated, mirrored, and then placed on the side of the center line. Thus, it has effectively indicated the convergence for the unrotated square on the y-plane. Now the larger bounding box of the rotated square can be placed by choosing a location for the near and far